Well, today we want to start looking at integral calculus, which is the reverse of differential calculus, reverse process, and we'll be talking about all the applications and meanings that flow from that. So to begin simply, I have two functions here labeled big F and little f. 2x, we know, is the derivative of x squared. Now, if I want to say that in reverse, I would say that x squared is an antiderivative of 2x. And you might wonder about why I say an antiderivative, because that implies there's more than one. And in fact, there is more than one, because if big F was x squared plus any constant, its derivative would be 2x. Alright, so a given function has a unique derivative, but a given function does not have a unique antiderivative. There's a whole what we call family of functions that the antiderivative can be, denoted by the plus c. Alright, so the process of going in reverse of finding the antiderivative is called antidifferentiation or indefinite integration, and we'll talk more about those terms later. And in general, we say that big F is an antiderivative of little f if the derivative of big F is little f. And of course we have some notation to go along with that. So we have the integral sign, which kind of looks like a stylized S. We have the function that we're doing the antiderivative of, called the integrand. Following the integrand, we have a designator to represent what we're differentiating with respect to, in this case with respect to x. And then over here we have the antiderivative, denoted by big F of x plus c, to show the entire family of functions. So with the example I had above, if I was doing the antiderivative of 2x, I would write that as the integral of 2x with respect to x. And the meaning of this again is, remember, what function has 2x as its derivative? Well, x squared does, plus a constant of integration. Alright, so integration or antidifferentiation is just the reverse process of differentiation. So we know we have a pile of derivative formulas. We therefore have the corresponding integral formula. So for example, the derivative of sine x is cos, which means the integral of cos is sine, plus a constant of integration. The derivative of tan is secant squared. So therefore the integral of secant squared, x with respect to x, is tan x plus c. Alright? You can reverse the power rule. Take a look at that in a second. E to the x, the derivative of e to the x is e to the x, so the integral of e to the x is e to the x plus c. That's a nice one. And all the other log and inverse trig derivatives can be formatted into an integration formula. Some basic properties of integration that we would use right away. Differentiation and integration are inverse operations of each other. So if I were to integrate 2x dx to get x squared plus c, and then did the derivative of that, I should get back what I started from. One undoes the effect of the other. The integral of a constant times a function is the constant can be brought out front times the integral of f of x, and the integral of a sum is the sum of the two integrals. Alright, let's just do a couple of antiderivatives just to get a feel for this. Now the first one involves powers, and when we did derivatives, we did have the derivative of the power rule, a variable to a constant, which was nx to the n minus 1. Now what I want to do now is be able to go in reverse. Okay? So if you just think about this for a little bit, what's going to have to happen is that the power is going to have to increase by 1. You're going to have to divide by the new power, and then add your constant of integration, plus c. I'll just squeeze it in there. Alright? Alright, so here we go. Now we have the integral of a sum, which means that we can integrate each of these separately. Okay? I won't write it out separately, but we're going to integrate x squared, then integrate 3x, and integrate 4. Okay? So what function has x squared as its derivative? That's really the question you're asking yourself. What function has x squared as its derivative? Well, that would be x cubed, raise the power by 1, and divide by the new power. Okay, remember, you can always ask yourself, if I did the derivative of this, would I get x squared? Okay. The next one, the constant is on its own. It can be brought out. And then x, I'm going to raise the power by 1 and divide by 2. Okay. 4. Okay. What function has 4 as its derivative? Well, 4x. And if you think about how that relates to this, the 4 can be thought of as 4x to the 0. So I've increased the power by 1, and I've divided by the new power 1. So it's 4x plus a constant of integration. Okay, so there's your antiderivative. This function, its derivative, would be the thing we started with. We're going in reverse. Okay, now let's apply the power rule to something a little bit more complicated. I want to integrate this function, which I'm going to write in exponential form. And I'm doing the reverse power rule. So I'm going to increase the power by 1, which is going to become x to the 5 over 4. Divide by that new power, 5 over 4. Minus, I'm going to increase the power by 1, which is x to the negative 1. Divide by the new power, negative 1, plus a constant of integration. And cleaning it up a bit, 1 divided by 5/4 is 4/5 x to the 5/4 plus 1 over x. Okay, that's positive. X to the negative 1 is 1 over x plus constant of integration. Okay, finally, let's look at a trig example. I want to integrate this function. So by one of my properties, I can pull the constants out front with respect to x. Minus 2 integral secant squared x with respect to x. And I say to myself, what function has sine x as its derivative? Well, that would be negative cosine x plus a constant. What function has secant squared as its derivative? Tan x plus a constant. And all of those constants are creating one constant, so I'm only going to write it down at the end. And so it's negative 3 cosine x minus 2 tan x plus c.